How does the XRD refill refinement method help in obtaining a detailed spectrum of materials like Na 0.95, Li 0.15, Ni 0.15, Mn 0.55, Co 0.102 cathode material? And what role do the P2 and O3 phases play in this analysis? How are the diffraction patterns of these phases interpreted to gain insight into the material's structural properties? What does the refined XRD spectrum of Na 0.95, Li 0.15, and Ni 0.15, Mn 0.55, Co 0.102 reveal about the material? And why are the P2 and O3 phases important for understanding its behavior in applications like sodium-ion batteries? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the schematic diagram of the crystal structure of P2 and O3 phases illustrate the layered nature of the material? And why is it essential to understand these phases when designing high-performance cathode materials? What specific features are analyzed in the crystal structure of these phases, and how do the structural differences between P2 and O3 phases affect the electrochemical performance of the material? How does the layered structure of the P2 and O3 phases contribute to the intercalation of sodium ions, and why is this an important factor in the material's effectiveness as a cathode in batteries? How do researchers use the schematic diagrams to compare the lattice arrangements of P2 and O3 phases, and what implications do these comparisons have for optimizing material properties? What challenges arise when refining the XRD spectrum for complex materials like Na 0.95, Li 0.15, Ni 0.15, Mn 0.55, Co 0.102? And how can these challenges be overcome through proper experimental design and data analysis? How does the combination of XRD refinement with schematic crystal structures enhance our understanding of material design and help in the development of next-generation energy storage systems? What can the XRD refilled refinement of materials like Na 0.95, Li 0.15, Ni 0.15, Mn 0.55, Co 0.102 teach us about the importance of precise structural characterization in material science, and how does it impact the overall performance and scalability of sodium-ion batteries? How does X-ray absorption fine structure XAFS spectroscopy work to characterize the local structure of materials? What role do the absorbed X-rays play in providing information about the sample, and how is this data used to understand the material's characteristics? How can the spacing between the absorbing atoms and their neighboring atoms be determined through XAFS spectroscopy? What information about the number and type of atoms can be derived from analyzing the XAFS spectrum, and how does this contribute to our understanding of the material's composition? How does the oxidation state of the absorbing element affect the XAFS spectrum, and why is it important to determine this state for understanding the local environment of the element?